is the second lecture for advanced thermodynamics, and today we will be taking up a numerical problem as shown on the text below. In this numerical problem, the question is based on Otto cycle. So first of all, we need to draw a rough sketch of an Otto cycle. So in Otto cycle, we are having 4 processes: process number 1 to 2, 2 to 3, 3 to 4, and 2 to 1. This is the PV diagram for an Otto cycle. This is an ideal Otto cycle. In process 1 to 2, there is an adiabatic, reversible adiabatic compression process. That means it's an isentropic compression process. Process number 1 to 2. 2 to 3, the process is constant volume heat addition process. 3 to 4, the process is isentropic expansion. And 4 to 1 is the constant volume heat rejection process. Following data are given in this numerical. First, temperature at the inlet, that is T1. The value of the temperature is in 35. It's in degrees Celsius. For that, we need to convert first into Kelvin. So, to convert into Kelvin, we have to add 273 plus 35, that will be equal to 308 Kelvin. After that, we have been given with the pressure at the inlet of the engine, that means at the initial stage of the compression, and it's P1 equals to 0.1 megaton. And when we convert it into kilonewton per meter square, it comes to 10 kilonewton per meter square. And we are given with compression ratio, that is 8, and gamma, that is equals to 1.4. Compression ratio is nothing but the volume. It is the ratio of the volume at the inlet of the compression to the volume at the outlet of the compression. Meaning to say, it's simply V1 by V2 is equal to RK. So these data are given, and first of all, from these data, we will be finding out the efficiency of an Otto cycle. The efficiency of an Otto cycle is represented as, or it is given by a basic formula, that is equals to 1 minus 1 by RK to the power 1 gamma minus 1. RK is compression ratio, and this is equals to 1 minus 1 by A to the power 1 gamma minus 1, that's equals to 0.4. And when we calculate it, it comes about 0.565. That means to say the efficiency of an Otto cycle is 56.5%. Now we have been given the compression ratio, and we have already discussed that compression ratio is nothing but the volume at the initial and the volume at the final compression, and it's nothing but V1 by V2 is equals to 8. It's given in the question, and we know that from ideal gas equation, that is PV equals to mRT. Here we are taking M as 1, and for that V1, from that equation, V1 comes equals to RT1 divided by V1. When we put the value of R, that is for air, it's 0.287 into T1. T1 value we have calculated it as 308 Kelvin and divided by 100. 100 is the pressure that is at the inlet of the compression. So pressure is given, temperature is given, we know the gas air constant R value, and then we can calculate the value, that is V1 value, as 0.844 meter cube per kg. After calculating the value of V1, we can calculate the value of V2 by simply V1 by V2 equals to 0.884 divided by 8, and it comes to 0.11 meter cube per kg. That's the volume at the exit of the compression. After that, calculating the V2 value, we will be calculating the temperature at point number 2. So, to calculate the temperature at the point number 2, we know the relationship T2 by T1 is equals to V1 by V2 to the power gamma minus 1. The process, since this process is the isentropic compression process, so for isentropic compression process, we have a relationship between temperature and pressure as written here. And we know V1 by V2 is equals to 8 and gamma minus 1 comes to 0.4. So T2 by T1 comes to 2.3. Now we multiply 2.3 with 308 Kelvin, and T2 comes to 708.4 Kelvin. After calculating the T2, we have been given the amount of heat added during the combustion process. So in the question, the amount of heat added in the combustion process, number 2 to 3, is 2100 kilojoule per kg. So we know from the basic equation Q1 equals to CV. Why we are taking CV? CV because the process between 2 to 3 is constant volume process. So for constant volume process, we have been given with CV value. We know we have to calculate T3. We have already calculated T2 here. And we know Q1. So from this relationship, we can find out T3. And T3 is equals to 3633 Kelvin, and T3 is the maximum temperature for the cycle. This also we have to calculate as per given in the question paper. We have calculated a T3 T max, that is T3, with that relationship. Now we have to find out pressure at point number 2. Again, for isentropic process, we have V2 by T1 is equals to V1 by V2 gamma to the power gamma, because the process is isentropic process, and for isentropic process, the relationship between pressure and volume is something like this. V2 by T1 is equals to V1 by V2 to the power gamma. We know V1 by V2 is equals to 8 and gamma value 1.4. We can calculate V2 by V1 equals to 18.37. We will have no unit for that because it's the ratio of the same unit. After calculating this ratio, we know the pressure at the initial of the compression, and it's already given as 0.1 megapound. So for calculating the pressure at point number 2, we will simply multiply 18.37 with this pressure, that is 0.1 megapound, and once we can multiply it, we get a pressure at point number 2, and that comes to 0.1873 megapound. So after calculating the value of P2, we know that process number 2 to 3 is a constant volume process. And for constant volume process, we have relationship as P3V3 divided by T3 is equals to P2 divided by P2 into V2. V2 and V3 are constant from this process, and we have relationship as P3 by T3 is equals to P2 by T2. We have to find out pressure at point number 3, and pressure at point number 3 will be the maximum pressure. We can calculate the simply pressure at point number 3 as 1.837 multiplied by, that is temperature 363 divided by 700, A equals to 9.426 megabar. That is the maximum pressure at point number 3. Now, net work, we know that the efficiency is nothing but work output divided by heat supply. So we have already calculated the efficiency of the cycle, and we know the heat supply, and so we can find out the net work. Net work will be nothing but equals to 1186.5 kilojoule per kg, and we know that net work will be nothing but P mean, that is mean effective pressure, into V1 minus V2 equals to P mean into 1.884 minus. So after calculating the value of P2, we know that process number 2 to 3 is a constant volume process. And for constant volume process, we have relationship as P3V3 divided by P3 is equals to P2 divided by P2 into V2. V2 and V3 are constant from this process, and we have relationship as P3 by T3 is equals to P2 by T2. We have to find out pressure at point number 3, and pressure at point number 3 will be the maximum pressure. We can calculate the simply pressure at point number 3 as 1.837 multiplied by, that is temperature 363 divided by 700, A equals to 9.426 megabar. That is the maximum pressure at point number 3. Now, net work, we know that the efficiency is nothing but work output divided by heat supply. So we have already calculated the efficiency of the cycle, and we know the heat supply, and so we can find out the net work. Net work will be nothing but equals to 1186.5 kilojoule per kg, and we know that net work will be nothing but P mean, that is mean effective pressure, into V1 minus V2 equals to P mean into 1.884 minus 0.11, and P mean will be equal to 186.5 divided by 0.774, that is equals to 1533 kilobar. And when we convert that into megapascal, it will come as 1.33 megabar. So this is the solution of the numerical problem. Thank you.